using, or whenever you're trying to prove that an identity is true, what you need to remember is that you don't assume it's an equation. What you have to do is you have to essentially work with one side of the equation, the left or the right. It's very rare we ever have to work with both. But essentially through manipulation of one side, you need to show that it's equal to the other side. So you cannot work with it as an equation. You're not solving. You're trying to prove that the statement is true so that the left is actually equal to the right. So just as a reminder, like I say, with identities, you are never working with both sides at the same time. You're working with one side, left or right, and you're trying to then prove it's equal to the other, the one that you haven't chosen to work with. All right, so we did do some identities in the first lesson or two of our trig stuff, using the grade 11 knowledge that we had to prove identities. So we have done examples like this, but that's just a little reminder for us. So if we have a look at our first example, all I've done here is I've just put the double and compound angle formulae here for us, because obviously we need to now start applying this stuff to our identities, to our equations, all of that. And because not necessarily everyone has a formula sheet in front of them during our lessons, I just thought I'd put it up, so we're going to use it. Okay, so this first question says, prove that 1 minus cos 2 theta over sine 2 theta is equal to tan theta. All right, so I've given you a few like tidbits of advice as we've gone along. But the first thing is you now need to decide which side you're going to manipulate. Now, I have said to you before, generally speaking, we always use the side that contains a tan. But the sign that contains a tan in this case is just a tan. So the only thing I could actually do on the right-hand side is say sine theta over cos theta using my tan identity. So while sure, you're welcome to do that, we can't do anything else. So what we now need to do is we need to have a look at our left-hand side and see if there's something more going on there that potentially is useful for us. And if you have a look on the left-hand side, you've got double angles. Now, because we've got double angles, we know that we can apply our double angle formula. All right, so I'm going to manipulate the left-hand side of this identity because there's a lot more that I can do on that left-hand side. So my left-hand side is the 1 minus cos 2 theta over sine 2 theta. All right. So as you can see, I've stated which side it is I'm going to manipulate, and now I'm going to go and do my cos 2 theta of a double angle. There's 3 potential formulas that we can work with. We don't know which one just yet we're going to work with. So what I'm going to do first is I'm going to change the sine double angle because there's only one formula. I can't question it. I can't make a mistake. I can only change it to 2 sine theta cos theta. So that means I've got 1 minus cos 2 theta over 2 sine theta times cos theta. Now, when you're proving an identity, and I've said this before, always go back to what it is you're trying to prove. So remember, what we're trying to prove is that this whole thing is equal to tan theta. And remember your tan identity that says sine theta over cos theta, okay, is equal to tan. Now, this little tidbit of information for us is going to be quite useful. The reason it's going to be useful for me is because what I see I have so far is in my denominator, I've got a sine and a cos. And in my numerator, I still have that double angle, but I know that I should be heading towards a situation where I have just a cos in my denominator and just a sine in my numerator. If I can get that right, I'm on the right track, because then I'm hopefully going to be able to simplify to just have a sine in my numerator, a cos in my denominator, and therefore I have tan. The other thing I just need to be mindful of is the fact that I do have this 1 in my numerator. That's not like a huge issue. And sometimes we might have to change that 1 in accordance with my square or Pythagoras identity. So sine squared plus cos squared equals 1. But if we can avoid that, we do. Okay, so based on what I've just said, I've got a sine and a cos in my denominator, which is okay because I want a cos in my denominator. But in my numerator, I need to get a sine. In order for me to get a sine over cos, I have to have a sine in my numerator. So that means if I look at my cos double angle identities, I'm either going to use the first or the third. Now, we don't really want to introduce a cos squared because now I'm just introducing a whole new term for myself. Ideally, if possible, I would like to just introduce a sign. So I'm going to go with the third formula here, and you'll see why that's also really helpful in terms of the 1 now. So we've got 1 minus, and now we substitute in our cos double angle, 1 minus 2 sine squared theta all over 2 sine theta cos theta. Now what you can see is that as I've replaced that double angle, when I distribute in that negative, the 1's cancel out. So actually all I have here is 2 sine squared theta in my numerator divided by 2 sine theta cos theta. Now try and not cancel these out too aggressively. Your marker or your teacher still needs to see what's going on. But what we now see is that 2 divides by 2, giving us 1. 1 sine theta in my numerator cancels with the sine theta in my denominator. And remember, the whole goal was to try and get a sine at the top and a cos at the bottom. And I've been able to do that through the substitution of my double angle formulae. All right, so what I now have, once I've simplified all of that, is sine theta in my numerator over cos theta in my denominator. And remember, according to my tan double angle identity, sine over cos is equal to tan. And what I have therefore proven is that the left-hand side is equal to my right-hand side. So I've said this to you before, there's no like special formula I can give you where I say, if you follow this step, this step, this step, this step, you will get the answer. Unfortunately, identities don't work like that. The thing with identities is that you need to start seeing, firstly, the formulas that you can apply. And you almost need to be able to think 1 step ahead of your actual working. You almost need to think, okay, well, if I were to substitute this in, what would it do to my expression on the left-hand side or the right-hand side, whichever side you're choosing to use? You need to remember your identities, so the tan identity and the squared identity or the Pythagoras identity. You need to remember that there are potentially times where you're going to have to factorize. There's times where you're going to have to find an LCD. There are times when you're going to have to use reductions and co-ratios. That doesn't come up a lot in identities, but there are times where you have to use certain bits of information from the whole of your trig section that we have learned. So in this case, just to remind you, because I knew I was working towards tan theta, and that's another thing, you always need to look back to where you're going. So you know what your end goal is. You know that your end goal for the left-hand side is to show that it's equal to tan theta. Always go back to where you need to be and see, okay, if I know I need tan theta, what does that mean I still need to get? And that's exactly what we did. We knew we needed tan theta, so we knew we needed a sine in the numerator and a cos in the denominator. How am I going to get those things to be what I want them to be? And this is now all just manipulation. And I've said that to you before. Trig is manipulation. That's all it is. All right, so let's take a screenshot of this one. Can't remember if there's another example, if there was a you try. Yes, there's another example. So let's take a screenshot of this. We'll try another one. I'm going to give you one to try by yourself, so don't stress. And like I said, guys, unfortunately, there's no like special rule, special formula I can give you that will work every time. It really is a case of you becoming comfortable with your trig content and your trig rules. Okay. So if we have a look at example 2, again, I've given you the information on the side, but we now want to prove that cos 2x divided by cos x minus sin x is equal to cos x plus sin x. So again, start looking for like things that sort of look familiar to you. So the first thing that I need to decide is which side am I going to manipulate. Now on the right-hand side, you've got a cos x and a sin x. You can't really do anything with those unless you want to introduce a tan, which as we know, tan is a bit of a outsider, okay? We don't really want to introduce tan unless we absolutely have to. So I don't really want to manipulate the right-hand side. On the left-hand side, I've got a double angle, so that's great. So I'm probably going to work with my left-hand side here because I know that I can substitute in a double angle formula for cos 2x. Okay, so we've decided which side we want to manipulate. Now we have to decide how to manipulate it. So remember, cos of a double angle, there's 3 options. I now need to decide which option is which. Now, if you go back to what you were given, cos x minus sin x and cos x plus sine x. Somewhere in the back of your mind, you should be thinking, well, that kind of looks familiar. Cos x plus sine x, cos x minus sine x, that sort of reminds me of a trinomial. And more specifically, it sort of reminds me of the difference of squares. Because remember, if, for example, you had x squared minus y squared, when you factorize that, you get x plus y and x minus y. That's kind of what we have. We have cos plus sine and cos minus sine. So we have a situation where factorization is probably going to be important here. Now, because I've gone that extra step, and because I know that my final answer, I need to have both a cos and a sine term, I'm going to pick the formula or the cos double angle formula that has both. And that would be my first formula. So to replace my cos double angle, I'm going to have cos squared x minus sine squared x all over cos x minus sine x. And what I hope that you notice is that in your numerator, you have the difference of squares. You've got a cos squared minus a sine squared. That's the difference of squares. So we can factorize that. We've got cos x minus sine x, oops, times cos x plus sine x. Difference of squares. In my denominator, I still have my cos x minus sine x, and you should remember this from your grade 11 algebra. We are now able to cancel out, whoopsie, the entire factor of cos x minus sine x. That's gone. The whole bracket divides away. And so what I'm now left with is just the bracket cos x plus sine x. And if you look to your right-hand side, that's exactly what we wanted to prove. Okay, so like I said earlier, sometimes factorization is something that we need to be able to deal with. Okay, it's not necessarily everyone's favorite, but we need to be able to deal with it. In this case, I knew that there was factorization because of what I've highlighted here in green at the top. I could identify that cos minus sine and cos plus sine had a relationship with a quadratic expression. It was the difference of squares. And so if I already had that in the back of my mind, I know where I need to go. I know I need to use a double angle formula that deals with the difference of squares. I know I need to factorize and therefore go and simplify. Okay, so these things, again, you just have to get more and more familiar with the terms you're working with. I'm not saying this is going to come naturally to you straight off the bat, and if it does, that's awesome, but it comes with practice. Once you start training yourself to see these different things, it does become a lot easier to prove identities. Okay, so take a screenshot, and guys, just remember, if you've got questions, please ask. I know I do a lot of talking, and it's just because we have to get through so much, but please ask questions if you're not 100% sure why I've done something, where a value has come from, where a term has come from. It's the only way we learn. Okay, if you don't feel super comfortable just unmuting and asking, just send a direct message to me on the chat. I'll help you, but please do ask. Yes, we're taking those off screenshots. And then I think this is another one where I've asked you to try. Yes. Okay, so there's a question here that I've asked you to try by yourselves. We want to prove this identity. Cos theta plus sine theta squared equals 1 plus sine 2 theta. So I want you to give this one a try. Think about what you have on the left, what you have on the right, and how you can manipulate it. And guys, I'm not saying all the time, but if you see a double angle, you're probably going to have to manipulate that side because we've got formulae that we can replace a double angle with. Okay, so that's a little hint for you. I'm going to give you 5 minutes. Let's give this one a try. And then we will have a look at the answer. If you've got questions while you're doing it, just ask. You're welcome to unmute yourself and ask, but let's give this a try. Okay, guys, I'm going to give you 1 more minute and then we'll have a look. If you need more time, also just let me know in the chat. Okay, excuse me, let's have a look. All right, so I hope we agree that we're going to have to manipulate the, actually could have done either. So I've actually given you both options here. So if you decided that you felt that the left-hand side was the best for you to manipulate, that's absolutely fine. So essentially what you would need to do there is you would need to square your brackets. So you'd essentially have to distribute out the binomial times the binomial. And what you would then need to identify in that case, as you can sort of see as I've color-coded, that once you've distributed, cos squared plus sine squared is your Pythagoras or your square identity. That gives you 1. And then in the middle there, that middle term of 2 sine theta cos theta, that's your sine double angle. And so you get sine 2 theta, which is equal to the right-hand side. If you didn't want to do that, you didn't have to. The other way you could have gone and done this is you could have manipulated your right-hand side. So you could have used the double angle. That sine 2 theta changes, sine 2 theta changes to 2 sine theta cos theta, as you can see there. And then what you need to remember is, again, your square or your Pythagoras identity. The fact that 1 can be changed to sine squared plus cos squared. Now, the reason you would want to do that is because, as you can see on the left-hand side, you've got a bracket squared. That comes from factorization. So we would need to change that, because what you then end up with is a trinomial. So in this step over here, you have a trinomial. And if you're not too sure where the trinomial comes from, imagine it like this. This is x squared plus 2xy plus y squared. There's your trinomial. So x squared is the cos squared, xy sine cos, y squared sine. Because it's a trinomial, you can factorize it. It factorizes to 2 identical brackets, hence why you can get the bracket squared. So guys, again, like the whole idea of maths in general is that there's not only one way to do it. So in this case, both of these answers would get you 4 marks. There's nothing wrong with either of those answers. As long as you are applying your formulas, your identities correctly, go for it. So I don't know if all of you only did it one way. I don't know if you saw that you could do it both ways. It really doesn't matter if you didn't. As long as you can do one of them, you're good. But there are multiple ways to prove an identity. It really just depends on what you see, how you apply it. All right, so I'm going to leave that there for a second, take a screenshot, and we're going to have a look at another example. Okay. All right, so if we have a look at example 3, we need to prove that 1 plus sine 2a over cos 2a is equal to cos a plus sine a divided by cos a minus sine a. And again, look at what you've been given. Start to think about, well, where did these things come from? How could I potentially get these terms and get these expressions? And that's going to help you figure out what you need to do. Okay, so first things first, we see that on the left-hand side, we've got double angles. Like I said to you earlier, 9 times out of 10, if you see a double angle, you're probably going to use that side. On the right-hand side, I've got multiple terms, but the problem is I can't really do much of those terms. It's not like it's a cos squared or a sine squared where I could use a square identity. There's not double angles there. So unfortunately, there's not a whole lot I can do on the right-hand side. So I'm probably going to manipulate the left. Oh, no, yes, right. Right, so my left-hand side is the 1 plus sine 2a over cos 2a. Now also, guys, if you have a look at your right-hand side, cos a plus a and cos, I don't know what I'm saying, cos a plus sine a and cos a minus sine a are reminiscent of factorized brackets. We saw that earlier. Remember when we did the difference of squares? Those look like the difference of squares bracket. So there's probably going to be some factorization that I need to do here. However, I'm going to start by changing the sine to a, because remember, there's only one formula for a sine double angle. So 1 plus 2 sine a cos a. And then I've got my cos 2a. I still need to decide what I want to do with that, but we're getting there. Alrighty, so cos 2a, we already know that we're aiming for a factorization situation. And ideally in my numerator and my denominator, I need to have a sine and a cos, because that's what I have on the right-hand side. So right now in my numerator, I do have a sine and a cos in the second term, but I can't actually factorize that situation in my numerator. In my denominator, I only have a cos of a double angle, but I could easily get a sine and a cos. I can easily get one, because if I use this first double angle formulae, I'm sorted. The numerator poses a bit of a problem because, like I say, right now I can't factorize it and it doesn't look like the numerator I want. But remember that sine squared theta plus cos squared theta is equal to 1. So that 1 I can actually replace with the sine squared plus a cos squared. So that's what I'm going to do. Right, I've got cos squared theta. Actually, let's continue to color coordinate here. So cos squared theta, and maybe I should use a, plus sine squared a. That's all from my identity with the 1, plus 2 sine a cos a, all over. And like I say, we're going to choose the cos double angle identity that has cos squared a minus sine squared a, because I know I can factorize that. And I know that it's a difference of squares, of which this denominator, one of the brackets of a difference of squares, is cos minus sine. Okay, now this numerator should look familiar to you. We just did an example where we factorized this exact expression. So we've got cos squared a plus 2 sine a cos a. I'm just rearranging my terms to look like a trinomial, plus sine squared a. All over my denominator, which is dots, which we'll deal with in a second. If you can't see the dots, or if you can't see the trinomial, feel free to use x's and y's. So this would be x squared plus 2xy plus y squared, all over x squared minus y squared. So use algebra if you need to. Just as long as you say let x equal sine a and y equal cos a, I then know what you're doing and you can use the algebraic form of this. However, I can factorize. The situation in my numerator factorizes to cos a plus sine a times cos a plus sine a. Like I said, we just did it earlier where we had cos a plus sine a squared in the bracket. And then we've got our difference of squares. So cos a minus sine a, cos a plus sine a. Obviously, if we're brackets in the denominator with the other way around, it really doesn't matter. Okay, so what we see is that a cos sine a and a cos sine a divide away, they cancel out. And so what we are left with is cos a plus sine a over cos a minus sine a. And if you have a look at your right-hand side, that's exactly the same. My left-hand side is equal to my right-hand side. All right, so again, I could see where I needed to be because I kept looking back at what I needed to get. I knew I needed to get a cos plus a sine over a cos minus a sine. I know that that comes from a factorization of sorts, either a trinomial or dots. So in my numerator, when I saw that 1, I knew I could create a trinomial. In my denominator, when I saw that cos double angle, I knew I could introduce a difference of squares because of the cos double angle formulae. And these are just things you need to start training your brain to see. Again, it's not super easy. It doesn't just happen. You have to do a lot of practice to start seeing these things. But once you start to see these things, you can sort of figure out a pathway for yourself that you need to follow to get the answer that you want. Right, again, guys, you need to jump in with questions if you have any. I'm just going, but if we have questions, just ask, whether it's on the chat, whether you unmute yourself, whether it's a message to me, whatever, just make sure you're asking questions. Okay. So like I say, screenshots, and then we're going to have a look at another. What might be you try? I did just go through these, but you know my brain. Okay. Example first. Okay. So example 4, we've got sine 4 theta minus sine 2 theta divided by cos 4 theta plus cos 2 theta is equal to tan theta. Now, guys, what I want you to just take note of is that sine 4 theta and cos 4 theta, that's a double angle, because remember 2 times 2 theta would give me 4 theta, but it's a double angle of a double angle, because if you don't know what I'm talking about, so for example, sine 4 theta could be written as sine 2 times 2 theta. That's a double angle. But remember, 2 theta is also a double angle. So there's quite a few double angle situations we need to be mindful of here. So just bear that in mind. Okay, so if we have a look at the situation, I think it's fair to say that the left-hand side is definitely going to be what I manipulate, because that's got all the double angles going on there. Tan I could really only change to sine over cos. Right, the other reason I know this is going to be the left-hand side is because remember, all of those angles are double angles. On the right, it's just tan of theta. I can't really manipulate that angle anymore unless I now wanted to introduce a half theta, which again, if I can avoid a fraction, I'm going to avoid a fraction. So I'm likely going to manipulate my left-hand side with all of those double angles going on. And remember, sine double angles, those are the nice easy ones that you can go straight to. And I would do that as my very first step because there's only one option. So I'm going to change my sine double angle, sine 4 theta. I've already sort of described to you what happens with that double angle. Expands to, no, apparently we're not going to work anymore. Expands to, sorry guys, it looks like I'm going to have to go a line down. 2 sine 2 theta times cos 2 theta minus, and that's sine 2 theta. I'm going to deal with just now because what I see is that now in my numerator, all of my angles are the same. That's quite useful because if I needed to factorize, remember angles need to be the same. So I'll deal with the sine 2 theta if I need to. Okay, cos 4 theta, like I said, I would need to make a choice in terms of what I want to do. But remember, in order to get tan, you would need to have only sines in your numerator and only coses in your denominator. Because of that fact, I'm going to go for the double angle identity for cos that only deals with cos. So this cos 4 theta changes to 2 cos 2, let's try that again, 2 cos squared 2 theta minus 1. And then we've got the plus cos 2 theta. Again, I'm not going to do anything with that cos 2 theta because now the angles are the same. They're both cos 2. Yeah, my brain. They are both 2 theta. Right, so now I can start thinking about factorizing. In my numerator, I could take out a common factor. So I've got a common factor of sine 2 theta. That leaves me with a 2 cos 2 theta minus 1. And in my denominator, I have a trinomial. So if I rearrange this, this would be 2 cos squared 2 theta plus cos 2 theta minus 1. So that's a trinomial. The reason I know it's a trinomial, imagine it algebraically. 2x squared plus x minus 1. Trinomial. So we can go and factorize that. Okay, so my numerator I've already factorized. Don't obviously need to do that again. Excuse the hardy dogs. But now my denominator, I'm factorizing that trinomial. So that factorizes to 2 theta minus 1 times cos 2 theta plus 1. And hopefully what you can see is through this factorization, I'm able to start simplifying. So I can cancel, I can divide away that 2 cos 2 theta minus 1. So now I've got sine 2 theta divided by cos 2 theta plus 1. Now remember, our goal, because of what we want here, is that tan theta, which means we still need to go and deal with those double angles. Because in order for me to get cos of a single angle theta, I shouldn't have any double angles going on. But now at least I've simplified what I'm working with. I'm not working with all of those terms that aren't factorized and all of that nonsense. Excuse me. Right, so we can now deal with the next set of double angles. Sine, I've only got one option, 2 sine theta times cos theta. In my denominator, I've got options for cos, but remember, I only want to end up with a cos in my denominator. Based on my identity, I only want cos in my denominator. So I'm going to pick again the formula that only deals with cos. 2 cos squared theta minus 1, and then remember, I still have this plus 1, plus 1. Now, minus 1 plus 1 is gone. So I've got 2 sine theta times cos theta divided by 2 cos squared theta. And what do you know? We can simplify. 1 cos theta, my numerator, cancels with 1 cos theta, my denominator. 2 divides with 2. And so I'm left with sine theta over cos theta. Sine theta over cos theta is in actual fact tan theta. And as we know, that's exactly what my right-hand side was equal to. Sorry, I'm trying to not move it too much. And so therefore, this is equal to tan theta. And so my left is equal to the right. Yes, this is quite a nasty one just in terms of the fact that there were so many double angles that you had to deal with. But it doesn't change the fact that we have to be able to deal with them. Okay, so deal with the first set of double angles, so those 4 thetas, see what you can simplify, see what you can factorize out, and then you deal with the next set. Don't try and deal with everything at once because you're just going to make your simplification way too tricky. But go step by step. Like I say, we knew we had to work with the left because there was the double angle, and we can keep simplifying from there. Okay, so this was not a particularly nice one, but it does show you how important it is for you to be able to work with the formulae and also do things step by step, not try and rush and do everything all at once, because often that just overcomplicates the situation. Okay, so take a screenshot, and then you're going to try one by yourselves. Yeah. Right, so give this one a try for me. Your formulae are down at the bottom there. So if you need it, have a look. Now, as you can see, there's no double angles, but there are compound angles on the left-hand side. So take a look, be mindful, give it a try. And remember, guys, if you have questions, please just ask. And we'll give you another minute or two, and then we'll have a look. Alrighty, grade 12, let's have a look. Okay, so like I said to you, we've got some compound angles going on the left-hand side. So even though on the right you've got the difference of squares, you have multiple terms that potentially could factorize. Just be mindful of the fact that that one throws us off, right? So it does create a bit of a problem for us when we start to think about how we could factorize. So because we've got the compound angles on the left, that's what we use. So just remember, you've got a cos x plus y, so that's the compound angle cos A plus B. And then in your second factor, you have got the cos x minus y, so that's a compound formula cos A minus B. So that's essentially what I've done moving forward in the next step. From there, it's not the nicest thing in the world, but you distribute. Now, it's really important, like I said earlier, to start to notice the relationships. You've got essentially a term minus a second term, so let's say A minus B in your first bracket times A plus B. If you have a situation like that, what you should recognize this as is the difference of squares. So yes, you're going to distribute everything out, but remember, difference of squares means that your middle terms cancel. If you were to distribute this, this would be a squared minus ab plus ab minus b squared. Those middle two terms eliminate each other. And so that's why when I distributed, I didn't even bother multiplying my middle terms. I just multiplied the first terms and I multiplied the last terms because I knew, according to difference of squares, that was going to happen. And you're welcome to do that. There is no need for you to do unnecessary work. So once you had that situation, sorry. Right, once you had that situation, you could now go a step further. Now, again, always be looking at what you are aiming towards. On my right-hand side, I'm aiming towards a situation where I've got a 1, but then I've only got sine terms. I don't know, it's not working. Got a 1, but only sine terms. So that means these cos squared x and cos squared y terms need to go. Okay, I don't want that. So what that means is now you need to think about that in terms of your square identity. So if you, okay, there's a lot going on here, but remember, sine squared theta plus cos squared theta equals 1. Remember that if you manipulate that to get cos squared theta is equal to 1 minus sine squared theta. And so you could go and essentially take cos squared x, make it 1 minus sine squared x, cos squared y, 1 minus sine squared y. So it's back to that square identity that you learned in grade 10. And then once you distribute that bracket again, you're left with the one that you want. You've got some like terms that are going to cancel each other. I can't speak English tonight. Cancel each other out, and you're left with exactly what you wanted on the right-hand side. So guys, I hope what you see is that, I mean, I keep saying this, but trig is basically algebra, just with sine, cos, and tan. Everything that we've done here, obviously except for applying the compound angle formula, is pretty much distribution, factorization, like terms. That's all algebraic knowledge. So trig relies heavily on your algebra, which is why it's so important that you do go back and revise your grade 11 algebra. But once you've applied the formulas of your double angles, your compound angles, your tan identity, whatever, it comes down to algebra. It comes down to the skills you've learned there. Alrighty, so again, this wasn't necessarily the nicest one because of the compound angles, but it is all manipulation. I want to say this was from a past paper. I can't remember which past paper it was now off the top of my head. I think it was either a year ago or 2 years ago, but this was a